right, section 1.2 is going to build on what we did with problem solving in 1.1. We're going to get a little bit more into the idea of looking at patterns in this section. And the first thing we're actually going to do is hit on quite a few definition kind of things so that we're all talking about the same thing. We know the definition of what we're referring to. So our first part here says the word conjecture. So you should have these notes printed out so that you don't have to write everything down. I'm going to assume that you've done that. If that's not the case, make sure you do before next time. A conjecture is a statement or a conclusion that has not been proven. So it's kind of like an educated or a best case guess, right? It's conjecture. It doesn't mean it's right. It doesn't mean it's wrong. It's just your best guess. A counterexample is actually something that proves a conjecture false. Right? Inductive reasoning and deductive reasoning are sort of opposites of each other. Inductive reasoning is a method of making generalizations based on observations or patterns. You guys use inductive reasoning probably most of the time when you get dressed in the morning. You say, it's been hot for the last 3 days, it's probably going to be hot again today, and you probably don't check your phone or the weather channel or whatever. You just get dressed assuming that it's going to be like it's been for the past 3 days. That's inductive reasoning, where you're making a generalization about what's going to happen based on already happened things that have already happened. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So this is something we specifically use, deductive reasoning, within mathematics. And within mathematics, I'm going to show you examples of both of these situations. All right, does everybody have all the details written in? All right, specifically we are going to look in this section at sequences. A sequence is an ordered arrangement of numbers, figures, or objects, and sequences are usually encountered as early as like early childhood education, like pre-K, kindergarten kind of stuff. At that scenario, at that point in time, it looks an awful lot like red triangle, blue square, red triangle, blue square, what comes next, right? Kids are looking at patterns in terms of shapes and colors, things like that. As we get older, the patterns become different things. Maybe they're patterns of dashes and dots and lines. Maybe eventually they're the patterns with numbers, and those are specifically the type we're going to take a look at, of course. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, with a rule that shows how to obtain each successive term. So it looks something like this. If I had the numbers 2, 4, 6, 8, 10, that's a pattern, right? And the way I would get the next term is that I would add 2. So the recursive formula would be add 2. Okay, it tells you whatever your number is, the next term is found by adding 2. Okay, that's a recursive formula. An nth term formula, or a general term formula, is a formula used to find the nth term in a sequence with no prior terms needed. Okay, so this is kind of like when you had equations given in an algebra class somewhere along the way. Somebody said, find y when x is 7, and you've got an equation and you plugged in 7 for x and it spits out a number for y. Okay? I don't need to know, even if I've got a series of numbers, like a table of values, I don't need to know all the values in the table. All I really need to know is what the x value is to find the y value. Okay, so that's a general term kind of formula. It doesn't establish a pattern. You can't necessarily see the pattern quite as easily, but you can find the 50th term a lot easier than if you were finding the 50th term by writing all the first 50 terms out, right? That would be cumbersome. So both sort of have benefits and drawbacks to them. We're going to take a look at a couple of different types of sequences, more than two, but today I think we'll only get to two. The first type of a sequence we're going to look at is called an arithmetic sequence. An arithmetic sequence is a sequence in which successive terms are obtained from the previous term by the addition of a fixed number. So the example that I just gave you with all the evens would be an example of an arithmetic sequence. 2, 4, 6, 8. I add a common value every single time and I can get the next one. That common value that I add is called a common difference. It's the fixed number added to previous terms to get successive terms in an arithmetic sequence. Okay? Now, it's important to realize that that number added could be positive or it actually could be negative. So it could almost feel like you're subtracting a number every time, because subtraction is really just the addition of a negative. Okay? So sometimes we kind of feel like this common difference could be adding or subtracting, like where it says added to, that the words added to could almost be subtracted, subtracted from or something like that, because we're adding negatives in there. The other type, let me give you an example here, just for another example. Perhaps you have this sequence that looks like this: 2, 6, 10, 14. What would the common difference be for this sequence? 4. And it would be an addition of 4, right, to get every term. And if I knew that, I should be able to find the next 3 terms or whatever, right? Yeah. If I had an example where it looked like subtraction, it might look something like this. What would the common difference be for this one? Yeah, it would be a negative actually, right? It would be -3. So we would actually say that the common difference is -3, whereas the common difference over here is simply 4. You could put +4, but it would be 4. So the common difference can be a positive number or a negative number. It actually could be a fraction too, or a decimal. It doesn't have to be whole numbers or natural numbers either. Most of the ones we deal with are going to be whole numbers, but they wouldn't have to be. Okay, another type of sequence we're going to take a look at today is called geometric. A geometric sequence is a sequence in which each successive term is obtained from the previous term by the multiplication of a fixed number. You multiply by it to get the next one. That number you multiply by has a name. It's called the common ratio. And we'll do an example. Oh, let me do an easier example to start with. How about, all right, what would the common ratio be on this one? Yes, multiplying by 3. So our common ratio would be 3. Let's do one that's a little bit more interesting, perhaps. Okay, so what does it look like you need to do to get from one term to the next term? It looks like you're dividing by 3, right? Does everybody see that okay? Looks like you're dividing by 3. But a common ratio is supposed to be the number that you multiply by. So what would the equivalent be to dividing by 3 if you're thinking about multiplication? Times by 1/3, or multiplying by 1/3. So instead of thinking about this as division, it's really more appropriate in terms of the definitions here to think about this as multiplication, and in this case it's by a fraction. It's by the fraction 1/3. So our common ratio actually here is 1/3, not 3. 3 is what we'll be dividing by. We need to know what are we multiplying by. Okay, so it's multiplication by 1/3. That would be our common ratio. All right, forgot where this fell. We actually are going to talk about one more type of sequence. I don't know if you've seen this one before or not, but it's an interesting one. Has anybody heard or seen of the Fibonacci sequence? Oh, I see like 3 hands. That's fantastic. Wonderful. right, the Fibonacci sequence is not arithmetic and it is not geometric. And it follows but it does follow a pattern, and it's actually quite common in nature. So the Fibonacci sequence looks something like this. Okay, so those of you who raised your hand and said you've seen it before, zip your lips. Okay, because you know the rule, or so to speak. Those of you who haven't seen this pattern before, do you see what the pattern might be? Any guesses? Adding what?
Because if you have 1 plus 1, that equals 2. If you add your 1 and your 2, that gives 3. Your 2 and your 3, your 5, your 5 and your 8, it gives 13. And then your 8 and your 13, it gives 1.
Very good. That's exactly what you're doing. The previous two terms are added together to get the successive next term. So in other words, if we wanted to find out what happens next, we would add 13 and 21 together. And what would we get? 34. So our next term would be 34. And we could keep doing this indefinitely, right? Obviously, it's a recursive formula, agreed? I mean, you have to know the previous two terms, in fact, to get the next term. So there's not a general formula here. There is a recursive formula here. But this is the Fibonacci sequence. It does occur in nature. One of the places that in the back of my mind, I'm pretty sure this is true, so don't quote me, but I'm pretty sure that the rings on the trees, like when you look at the ages of the trees, follow Fibonacci sequence. You see lots of patterns with nature that have Fibonacci patterns within them, Fibonacci sequences. This feels misplaced. Every time I teach this lesson, and this is here, I feel like it looks like all of a sudden we changed gears in the middle of a lesson. But it's used in what I'm going to do next, so I'm going to put it here anyway. This is the definition of an exponent. So the exponent is a to the nth power. So if n is a natural number, so natural number again means counting number, 1, 2, 3, 4, and so forth. Then a raised to the n power is a times a times a, so forth, n times. And by definition, if n is 0 and the base a is not, then a to the n, which would be the equivalent of saying a to the 0, is 1. This is a definition of exponents. All right. Once we have those written down, we're actually going to see some examples of sequences. All right, so here's an example. It wants us to list the next 3 terms in the sequence. The second thing is to identify if the sequence is arithmetic, geometric, or neither. So parts 1 and part 2, we've talked about how to do that already. Part 3, we have not talked about at all yet. How to find the general term for the sequence. Okay? So go ahead and take just a minute. I would like for you to look at part A and part B, and I'd like for you to find the next 3 terms in the sequence based on what pattern you see, and to make a decision, is this arithmetic or is it geometric? We'll do part 3 for each of them together. Okay? Once you've done part 1 and part 2 for parts A and part B, look at a neighbor and say, this is what I got. Did you get that too? So let's compare what we have. Okay, when you're done, and we're get about 50%, maybe you're done at this point, compare with a neighbor. Do you have the same next three terms? Do you believe that it's arithmetic or geometric? Do you agree? Or neither? Okay, I see lots of heads nodding, so you must be in agreement with one another, so that's a good place to start. What are the next three terms in part A? So what pattern did we notice there? That we added 3. So if we added 3, is it arithmetic or geometric? That is arithmetic. All right, we'll come back to the part 3 on this one in here in just a second. Let's do the other part you guys did together. What are the next 3 terms on part B? Excellent. And what did you do to get from one term to the next in that sequence? Multiplied by 2, which makes the sequence geometric. All right, so what I'd like to do next then is to show you with these examples as my guide how we create the general term. Okay? Now, let me just say in advance that if you go to your book, it's going to show you a formula, and you can memorize the formula or whatever, and you can do it that way. That's one option. I don't like formulas very much, because if you memorize this, you're going to remember it for long enough to regurgitate this on a test, maybe. Maybe you're going to write it on a note card so you never even actually memorize it, which means you can't use this in the future. Okay? So I'm not a huge fan of let's go memorize a formula to figure out how to do this. I'm a much bigger fan of figuring out how the process is working so that you can create it anytime you needed to, if you ever needed to figure out a pattern anyway. Okay? So let's take a look at how to do this, because it's not that difficult, truly. Okay? So you've already told me that the pattern here is that you add 3, correct? All right, so think with me. Every time you add 3, and you add 3, and you add 3, and you add 3, so it sounds a lot like this is repeated addition. Does that make sense? Well, when you were in elementary school and somebody started talking about adding 3 together a whole bunch of times, if you wanted to add 3 together 7 times, in 3rd grade you learned a shortcut for doing that. What was that shortcut? Multiplication, right? Well, we're going to apply that concept here as well. Instead of adding 3 together a bunch of times, we're simply going to take 3 and multiply it by n, the number of times I'm wanting to do this. So this is where I'm going to start. 3n. So whatever you're adding or subtracting, like I could put this as a negative in here if I were actually subtracting a number, right? Or adding a negative. I could make this a -3. That'd be cool. You can do that. And you're multiplying it by n. And n is representing the number term you're on. Now take a look. Your first term in this sequence is a 1. Agreed? But if I put n equal to 1 in the formula here, I don't get the first term 1. I get 3. So I would subtract 2 off so that I would get the number 1. In some sense, this is almost like you're doing just this tiny bit of deductive reasoning, right? You're just a little bit of guess and check. And you can, in fact, guess and check to make sure you did it right by using the second term or the third term or whatever. This term is n equal 2. If I put 2 in here for n, 3 times 2 is, minus 2 is, do I get the term I wanted? I do. We can check it again. What if we put n equal to 3? 3 times 3 is, minus 2 is that my third term? Yes. So this is my general term for my sequence. 3n minus 2. It's always the common difference that I've added or subtracted times n, and then add or subtract whatever number I need here at the end, this plus 2, minus 2, plus 7, minus 6, whatever the numbers are, to get the first term. Okay, so that's how you find a general term for an arithmetic sequence. So let's figure out how we find a general term for a geometric sequence. So this sequence, you told me, is multiply by 2. Again and again and again. Times 2, times 2, times 2. You're going to multiply by 2 like 16 times or whatever, right? Well, again, somewhere along, I don't know, it's probably about 5th grade, you learned a shortcut for repeated multiplication. And what was it? Exponents. And that's exactly why this definition showed up right here. That's what an exponent is. It's repeated multiplication. So again, instead of repeatedly multiplying something, we can write it in an exponential form. In this case, our number was 2, and we're going to raise it to a power. And for convenience sake, and I'll explain why, we're going to write that power as n minus 1 instead of n. Okay? Exponent will always be n minus 1. You can just know that that's the exponent, and the base of your exponent is going to be that common ratio, in this case the number 2. Because what happens if I plug in n equal to 1 here? What's my exponent going to be? If I plug in n equal 1 into here, it's going to be 0. Which means I've got something raised to the 0 power. And what is anything raised to the 0 power? 1. 1. Remember, that's our definition over here. Anything raised to the 0 power is 1. Okay? So I have put the n minus 1 as my exponent so that every time I plug in n equal to 1, this expression that I have right there is always the number 1. And here's then what I do. I put the original first number at the beginning. Was it 3? Yeah, it was 3. This is my first term. So I have 3 times 1. And 3 times 1 is in fact 3. Let's try it with a different n value. Try it with n equal to 3 just for fun. If I put in n equal to 3, my exponent is 3 minus 1, which is 2. And then I have the 2 squared, which is 4, times the 3 at the beginning, which is 12. Is my third term 12? Yes, it is. So our sequence, I've kind of made our general term, is 3 times 2 to the n minus 1. It's always the first terms first. That's my 3. The common difference is next. That's the 2 in this case. And the exponent stays the same for every problem, n minus 1. All right. This kind of reasoning, is it inductive, going from patterns to general, or is it deductive, going from a general formula to finding specific values? Which one did we start with? Did we start with patterns, or did we start with a formula? We started with patterns, and we said, because I have these patterns, come over here again to remind you, one more back, because I have these patterns, and I want to make a generalization, right, I created these equations based on these patterns, is this inductive or is it deductive? It's inductive. I started with a pattern and I created a generalization. This is inductive reasoning. Started with a pattern and I made a generalization. All right. Example number 2 goes in reverse in some sense. On this one, I'm given that general term. And I'm asked to do some things. The first thing I'm asked to do, it says, using the nth term given, find the first 5 terms of the sequence. The second thing it says is to identify if the sequence is either arithmetic, geometric, or neither. So we're going to find the first 5 terms of the sequence. In other words, I'm going to let n equal to 1 and see what I get. And then I'm going to let n equal to 2 and see what I get, all the way till n equal 5. Okay, so I want you to do that. And then after you've done that, I want you to decide, is the sequence arithmetic, geometric, or neither? And again, you're going to compare with a neighbor. Okay? Okay, so you should have 5 terms, and you should have the statement arithmetic, geometric, or neither. And once you have that, and your neighbor does, compare. All right, have we compared with a neighbor? It doesn't look like a lot of comparing going on. Are people still listing out numbers? right, what happens when you plugged in n equal to 1? It was 0? On the first one? Okay, I was like, wait a minute, I'm concerned now. 5 times 1 plus 6, what do we get? 11? Okay, good. Oh, these are running into my numbers. Hang on, let me scoot these over. Okay, and then we plugged in 2, and you got 16, and then you plugged in 3, and you got 21, and then you plugged in 4, and you got 26, and then 5, you got 31. Okay, so whether you showed all of those additions or not was not necessarily the point, but these are the 5 numbers that you should have gotten. And did you find out, is it arithmetic, geometric, or neither? Arithmetic. What was the value you added every time? Yeah, it was plus 5. They didn't ask you to write that down, but just as a mental note, that's how you should have made your decision. And if you actually come back over to the equation, do you see why it's arithmetic from the equation standpoint? Because it's 5 times n. It's repeated addition, right? Repeated addition looks like multiplication. So that's what's going on there. Now on the second one, if you plug in the n equal to 1 and so forth, weirder things happen. I think that's why some of the conversations were a little bit more like, I don't know, I think this is what I'm supposed to do. Because it is a little bit weirder. So if I plug in n equal to 1 here, I have 1 squared minus 1, and I get 0. And if I plug in n equal to 2, what do I get? And if I plug in n equal to 3, excuse me, what do I get? 8. And n equal to 4, I get 15. And then n equal to 5, I get 24. Okay, so these are your 5 numbers that it was looking for. Whoops. 0, 3, 8, 15, 24. Is this arithmetic, geometric, or neither? It is neither. It can't be geometric, let's just say that right off the top, because there's no number I can multiply 0 by and get anything else. So geometric gets like whammied right off the bat. It's off the table. And then once you start looking at addition, you actually add. There's a pattern in how you do the addition, right? But it's not the same thing every time. So I don't go from 0 to 3, add 3, and then go from 3 to 8 and add 3 more. I'd have to add 5. So the addition has a pattern to it, and we'll talk more about that kind of pattern and what that is next time, but it's not arithmetic, okay, because it's not the same value added every time. Is this kind of reasoning inductive or deductive? This one's deductive. I started with a formula and I created my patterns. I started with an equation, a set of rules, that is the rule that I'm using, and I made the pattern. And that's deductive reasoning.